So here we go. So last time we presented the syntax of first order logic, and like I said, syntax means you, for any language, you start with the alphabet, you say how to make the words and how you put the words together to make sentences. And this is what I called the language of statements. And then I said instead of statements, we'll be calling them formulas. So the syntax specifies how the formulas of first order logic are built. And the way we specified this was to first specify some parameters. The language is specified by a triple countable set of the C stands for a supply of constant symbols. Then you have function symbols, and then you have predicate symbols. And from these, you start defining a set of terms of the language. So you have terms of L, which is defined by constant. Then you have a bunch of variables that you fix. Built inductively. Where f is a k-ary function symbol in f. Okay, so you take function symbols and apply them to terms that have been built inductively, and you get this is the set of terms of the language. And once you have the terms of the language, you define the set of formulas of the language. Which you start with equality. So you given any two terms, you can say two terms are equal, and then you have you take, if you have a predicate symbol of arity m, and if you have inductively built, you already have some m terms, you can talk about the relation, m-ary relation holds on these terms, and those are the atomic formulas. Which you close under negation, disjunction, conjunction, implication, equivalence, and then quantifiers. And that's it. This defines the syntax of formulas. This tells you. And then what we said is that now if I take any particular formula, you can represent it as a tree whose root contains, or any non-leaf nodes contain, are labeled by either connectives or quantifiers, and the leaf nodes are labeled by atomic formulas. So that's a tree structure that you can impose on the formula. And what you have again on the leaves, you have equality or predicate symbols, and they apply to terms. Now terms themselves can be again envisaged as trees whose non-leaf nodes are labeled by function symbols, and the leaf nodes are labeled by either constants or variables. Now why do I do that? Just to say that there is a structure, right? A tree has an inductive structure. What's an inductive structure of a tree? It's got a node and it has got subtrees, right? And then you go into subtrees, which again you keep going inductively down until you have a leaf node which doesn't have any subtrees, right? Which is only itself. So you can see that the syntax is defined inductively. And this is a standard terminology, and it's good to get used to this terminology, because now when we talk about doing any proofs, when we are actually doing any proofs on the set of all formulas, you can say by induction on the structure of the formula, right? So it's like instead of mathematical induction, one thing of course you can always do is associate a number with any formula, which you can always do, which I denote by alpha, which is the number of number of nodes in the tree representation of alpha. Is it visible? If something is not visible, tell me, I'll restrict myself to the visible portion. Okay, so you can always do it with numbers, but in any case it's on the number of nodes. It makes sense to always talk about by induction on the structure of the formula, so that it's really subtree induction that we are doing when you do that. Yeah. Any questions about this? Some people wrote to me that they are not used to trees and algorithms and so on, and well, the point is that I mean, if you are not interested in algorithms, you can get by. There is plenty of mathematical stuff that you can understand, but I think it would be useful to actually learn algorithms as you go along if you are interested. And for those who are learning any theoretical computer science, I would say it's absolutely essential to understand the algorithms as you go along and write the algorithms, look at the running time. But if you have any questions related to that, you can feel free to ask me. Okay, so and then we said, okay, there is with the syntax, there is a straightforward algorithmic question that comes up in front of you. And what is that? You given a string in this alphabet, which uses function symbols, predicates, whatever you have in your vocabulary, and then parenthesis, equality, negation, all these symbols, you get strings, and you want to know whether it's a well-formed formula or not, because you can write junk using this. So you need a way of parsing anything where you have syntax. There is always this question of parsing, and the algorithm, then what does it do? It just goes down the string in whatever order you like and tries to construct the tree. If it succeeds, it says yes, this is the formula, and if it doesn't succeed, it gets stuck at any point, it's going to say no, it's not a well-formed formula. And that's something that it's linear in the number of nodes of the tree. So linear in the size of the formula. The size of the formula is the number of nodes in the tree representation. So this is what we say. And so please make sure that you understand this style of Auringale. Yeah. Huh? So make sure that you understand the style of inductive definitions, because this is going to be the norm that we will use throughout. What, of course, that we need now, we now have formulas, and we have to talk about the meaning of these formulas. Right now they are just symbols. Remember that it is very important to realize that what we have got are constant symbols, function symbols, predicate symbols. These are just symbols denoting some constants or functions or relations that we have in our mind, right? Like I said, there is no, the 0 here is only a symbol denoting 0. Like in arithmetic, we always say that, there is a numeral and a number, right? 3, right? When I write like this, it's a numeral, it represents the number 3, right? The number 3 itself is the cardinality of the equivalence class of sets that contain 3 elements, right? So that's the number 3. So it's good to always keep in mind what you are talking about in terms of symbols. There's a symbolic representation, like pi is a real number. There is a decimal representation of that we make a lot of fuss about, but starts with 3.14 and some various things happen. We don't know all the digits. Yeah. So this is those are all representations, the syntactic ways of writing down the actual number, but the number itself is a mathematical object, right? So we do want to look at the meaning of the sentences of this language, and that is the idea of semantics. We want to specify the semantics of a logical language. Somebody gives you this, the logic is fixed, the set of all formulas is fixed. Now we want to give the meaning of the sentences in the logic. Okay, so for that, how do we go about giving semantics? Well, we already said that whenever I take a formula, intuitively we have some understanding, right? I mean, after all, if you're talking about the language of arithmetic, the language of graphs, the language of sets, what have you, we have some notion of some statements being true and some statements being false, right? I mean, 2 plus 3 equal to 5 hopefully is true, right? And so on. Now, the thing is, how do we say that an arbitrary statement given in this language, a formula of this language, how do we assign it as true or false? So this is a question that we are going to look at. So now, suppose let's work with our standard language of arithmetic. Consider various formulas, okay? Statements or formulas as we call them. So here is this, right? For all x, for all y, or what about this statement? I am talking about in the language of arithmetic, where I write this to mean the set of primes, this to mean the set of odd numbers. Well, for all x, prime x implies odd x. Well, hopefully, yeah, is it true?
False. False.
Why is it false?
Sir, because 2 is a prime and
Okay,
2
so
is not an odd.
can I say it's mostly true?
Yeah.
I mean, come on, there is one counter example, right? Almost true, but it's not true, right? Okay, it's not true, it's false, but I would say mostly true, if you like. What about this? Every prime number is green. What about this? What is green? Now, this is completely meaningless. Okay, so there can be all sorts of things about whether a statement is true or false. You know, calling it true, calling it false, you may have a lot of attitude about this whole business, right? And you might say, well, you could probably define numbers to be green or red or whatever for whatever properties that you choose. It's up to you, or you can say it's nonsense, right? Well, if you move to ad hoc languages, there is a lot more fun to be had, right? Okay.
So
Yeah.
I have a question.
Yeah.
So when we say a statement is mostly true, is it accepted as a conventionally correct logical term? Because mostly sounds a little vague.
Of course. Yeah. So that's why I put it within quotes, right?
Yeah.
I put it within
So
quotes.
this is just for the sake of understanding that we are using, or because I think in your first lecture also you had said something like statements can be mostly false or mostly true. So I'm just asking whether it is conventionally accepted by the logician as a valid term and it actually means something, or is it just for the sake of understanding that we're using it for now?
You decide. That's the point, right? Semantics meaning is what you give to statements, right? If you decide that you're going to give statements the meaning of just true or false, then of course there is nothing like meaningless, there is nothing like mostly true, any of these, right? So, and that's part of what I want to discuss and for you to think about, that what is the meaning that we want to give statements, right? Now, in mathematical logic, considered as if you are going to talk about the truth of statements in mathematical structures, well, typically we'll first at least start with only thinking about having only truth values as true or false. But the point before you do that, it's good to keep in mind where you might want to worry about all these things, right? I mean, for instance, look at this. For all x, large x implies large x minus 1, right? Where minus is a function symbol, I am not writing it as minus of x comma 1. What is this statement? What does this say? It says if a number is large, if a number x is large, surely x minus 1 is large as well, right? What about ten power 10? I say it's large. What do you think? Is this true or false? Yeah? Let's have a vote. How many people think it's a large number? Yeah, this is true.
So we have to define what you mean by large.
I don't know. I'm asking you whether you think it's large or not. Do you need a definition to say that this is large or not? Come on. So that's why I'm asking you. How many people think that it's a large number? Okay. Well, I would like you to give me a definition by which this is not a large number. Yes, Jenny? Jenny Jacob is the person I'm asking. Is it a large number? It would be very difficult to think of any sense in which this is not large, right? Or you are defining large in a way that is truly bizarre, I would say. Yeah? Yes, Jenny, come on, so tell me. Would you say this is a large number? 10 power?
No, but the domain may depend.
Well, I'm just talking about language of arithmetic, natural numbers.
Natural numbers, okay.
Yeah?
No, I'm not sure
Well,
what to say.
you are not sure what to say. Okay, fair enough. Yeah. So, yeah, the point is intuitively, it makes sense to say that a number like this is large, right? What about this statement here? Aditya? I'm talking to Aditya Subramanian. Yeah, Aditya S. Right. Yeah? Yes, Aditya?
I guess looking at that, I would say asymptotically they're both the same. So if one is large, the other is also large.
Yeah, I mean, if 10 power 10 is large, surely 10 power 10 minus 1 is large as well, right? Is there a meaningful sense in which you can deny the truth of this? But if you put these two together, what happens? Yeah? What would you conclude from these two? Yeah, well, I mean, I think from these two you should be able to see somehow we can actually infer that the number 0 is large. Yes, Siddharth? Yeah. Because you have said for every number, if it's large, its predecessor is large. So if 10 power 10 is large, you're going to come down to, right? So I think what I'm trying to say is that there is no meaningful sense in which you can deny that 10 power 10 is large. But if you accept this and if you accept that, you're going to come to a conclusion. In fact, this is the problem with logic that you're most worried about. You know, banning these kind of statements is really not a problem, right? This is, and calling this really false, you know, say this is, no, I don't care for mostly true, right? And this, you write junk, you live with junk, I don't care, you know, I choose this to be true or false, right? No problem, right? Who cares? I mean, meaningless and all is in your head, right? Garbage in, garbage out. I don't care. But this is a real problem. Because don't tell me that because you're a mathematician, you're going to avoid talking about something being large and small and so on, right? That's complete nonsense, right? If you believe that you're so precise that you'll never ever use terms like so there. So and so a predicate like this is what people would call a vague predicate. A vague predicate not as a value judgment, right? To say that, oh, you are being vague and I'm being, no, not in that sense at all. To say that there is a, difficulty in giving a judgment to it as true or false, right? What I would like to do is to give only a judgment as true or false to statements, to mathematical statements, and these are mathematical statements, right? But there are some mathematical statements that are difficult to pin down, and let's be clear about it. And I'm not talking about statements like happy and sad and so on. Those are, of course, difficult to give meaning to, but this is a good enough example to point out that vague predicates are interesting. Having said that, we are not going to talk about vague predicates, how to give meaning to vague predicates and so on, right? I just want you to keep in mind that there is something interesting going on here, and don't completely throw it away, right? Something to worth thinking about. Maybe we can look at these things later as required. So we are going to take a very, very narrow approach, something like what who was saying Megha was talking about. I don't want any of this kind of things. I just want to take the set of statements. I want to use the structure to tell me whether a particular statement is true or false, and that's it, right? Only. No mostly true. I don't want to say, oh, this statement is nonsense. No. You give me any statement, I want to label it true or false. And even then, it's very clear, it depends on the particular structure that you have got, right? I mean, for instance, for all x, right? I mean, this is true in a structure which has no maximal element, otherwise it is false, right? For all x, there exists y such that, right? This is true. This is not true over natural numbers, but it is true if what the structure that you are looking at happens to be real numbers. So and this is something that seems obvious but not taught in school at all, right? When you learn mathematics in school, you think of a mathematical statement as being true or false, but you don't quite say, this is true in some particular structure. So that is the entire what this is all about. Truth, so we'll formalize this by saying that we take the set of statements in our language, right? And truth is actually a relation. Truth is not something about a judgment, right? That it's true or false, but it's simply a relation between structures and sentences or statements. So this is the main idea, and let's build this up. So fix a logical language L. So truth we define as a relation between structures and statements. So formally, we will write this, the relation is defined this way, a vertical line with a double turnstile as it's called. So where you have a structure and a statement. Okay. So, or you write it as a binary relation, you could write this as this. But we all prefer the infix notation, right? So this is the relation that we want to define. To define that, we have to define the notion of a structure. What is a structure? What is a mathematical structure? Well, we said L, what is L standing for? language of something, right? Language of arithmetic. For the language of arithmetic, what is the structure of interest? The number line, right? The number line keeps you busy, right? I mean, you have natural numbers, rationals, reals, you have the field of complex numbers, right? You have number systems. Or if you are talking about the language of groups, the structure that you are looking at is the class of all groups. If you are looking at the language of graphs, the structures of interest are the class of all graphs, and so on, right? So given L, the notion of an L structure is defined to be, look, we want to define it in as general a way as possible, right? We don't want to have a definition each time a new structure comes along. So this is the whole idea of the enterprise that we have got. We want a language to describe all of mathematics, to talk about any mathematical structure on earth, right? So what is that structure as far as we are concerned? What is it doing for us, right? Well, if it is arithmetic, then the plus that I am using is actually the addition function. That's what you want to say, right? The dot that I am using in the language of groups is really the group action. This is all that we want to say. So that's all that an L structure is doing for us. Okay. So an L structure is defined to be, so for that, what is it that I need? First thing is, somehow I have to talk about the elements, right? In the language of arithmetic, I have to pin down numbers, right? So I have to talk about the set of natural numbers, set of real numbers, right? Some domain where the elements come from. When I say x and y and so on, those x and y live in some domain, right? So a structure is defined to be, first let me write it as a pair, S equals, where D is called the domain, which is simply a set, some set, right? Which will give meaning to the elements of my language. And then this little, so this is the Greek symbol iota, and how I write, hopefully you have better Greek skills and can write it better. This stands for the interpretation function. We have to interpret the symbols that we have chosen, right? So for instance, what you have written as ZERO, you want to interpret as the number 0 in that set, right? In the language of arithmetic, D is simply the set of natural numbers, or like I said, in the whatever language that you have chosen, some mistake, right? In the language of order, it's simply the set on which you are imposing the order, and so on. Okay, so I itself is given as a triple, naturally. An interpretation for constants, an interpretation for function symbols, an interpretation for predicate symbols, right? We need interpretation for all these things. Like, because in the predicate symbols you might have written green, right? And then you have to give meaning to that. You have to interpret when a number is green and when it is not, right? That's your problem because you defined it, right? You have written a binary relation EXY, right? That binary relation E has to be interpreted as the edge relation on the graph, and so on. So what is the interpretation for constant symbols? This is very simple because every constant is actually an element of the domain. So it's simply a map from C to D. This is just a regular D. Is this clear? Okay. Now what will be a function interpretation for function symbol? This maps every k-array function symbol. I hope you know this notation, right? You take an element of the domain and say, show how that acts on it, right? It takes a k-array function symbol, and what should it map to? What would be the meaning of a k-array function symbol? What do you think it should be? Yes, Ananya? it takes a k-ary function symbol, and what should it map to? Yeah, sorry?
The domain.
Something on the domain, right?
Yeah, something.
Yeah, so it should be a function on the domain. What kind of function on the domain? So, suppose this is plus. Suppose this is plus, right? Which is a binary function symbol. What should it map to?
D squared.
D squared to a map from D squared to D. So what we are talking about? Yeah, it takes a k-ary function symbol and maps it to a k-ary function on the domain. That means take k-tuples of elements of the domain and produce an element of the domain. All the action is on the domain D. That's why this is the structure. So notice this is what you mean, right? And this is very general. It doesn't matter what language we use. Okay. The next one should be very clear now. How do you give a meaning to an Emery predicate symbol? Note that it means a relation, right? An Emery relation. So what should you have? It takes an Emery relation symbol. Yes, Siddharth? What should I have here now? I'm going to take m tuples and
D raised to k.
sorry?
D raised to m
To?
True or false?
To true or false or 0 or 1 or whatever, right? Emery relations, whatever is your favorite way of denoting. Yeah? 0 says it's not in you present an m tuple, right? If this interpretation gives you 0, it means it's not in the relation. If it's 1, it is in the relation. This is it. By now, you have given any parameter. For every parameter, you have given an interpretation. So this is the notion of a structure, an L structure. An L, remember the language is parameterized by whatever is the vocabulary that you have chosen. A structure is simply an interpretation for the vocabulary. Nothing is that, it can't be more straightforward than this. There's a lot of notation, but it should be very clear that from this you can actually interpret all your. Is this clear? Yeah? This is the notion of an L structure. Now, in a structure, I can talk about how a statement is true or false within that structure, and that is the definition of this. For doing that, well, remember something that's going to come up now. Remember that I said this is the language of statements, and I started calling them formulas. We'll see that there is a slight difference. Here is an example of a formula. Kind of statement that you might write. What is this saying? If take any x, if P holds for x and Q holds for y, then x and y are in the relation R. How do you give meaning to this statement? What's the problem here? Yeah, there is a y floating around, right? As opposed to a statement like this. Oh, by the way, so there are some nice statements that we should think about. What about something like this? What about this statement for all x, for all y, x equal to y? I don't know, some structure. Is it true or false in a structure? Can somebody read the statement and tell me what it means? It says, take any elements x and y, they'll be equal. What kind of a structure is it talking about?
Structure has only one element?
Exactly. Thanks, Jenny. Yeah. This says that the structure has exactly one element. Your domain is a singleton. If the domain is a singleton, it's certainly true that take, or what else?
It could be empty.
It could be empty, absolutely. Thanks, Shubhankar. Yeah. So it says that your domain has at most one element. Domain is either empty or that's not a problem. So you can give meaning to statements like this. What about statement like this? Well, what about the truth of this statement? Depends on y, right? It depends on what meaning you give to y. The moment you fix y, then I take any x, check if p holds for x and q holds for y, then I can check whether x and y are in the relation, right? So, and this is a notion that logic books will give a lot of fuss about, pages are filled with this. Y is a free variable, right? Y is occurring free in this. We'll see this. I mean, this is something that you have to get used to. You will say x is a bound variable because it has been quantified, y is not quantified, so it's occurring free. So you have to give meaning to a state. That's why you call them formulas. Formulas in general can have variables floating around like y. Statements or sentences, as we call them, are those which where are things of this kind where there's nothing free floating around. But I'll define all this for you, but I'm just telling you that this is something to keep in mind. Now we want to, the whole point is after all to talk about truth of formulas, right? Whether a formula is true or false, right? So what is the simplest formula that you can start with? Well, look into your inductive definition of formulas. How do you start defining formulas? Atomic formulas. In atomic formulas, what are the simplest formulas that you can start with? Equality. Equality, right? Suppose, and okay, equality, well, I have y squared. I might as well write. So that's a t1 equals t2, right? This is a term. X cubed plus y cubed is a term and z cubed is another term. This happens to be there in my language, and I have interpreted this actually stands for x dot x dot x, right? With appropriate parentheses plus y dot y, and this is z dot, right? And I have, let's assume that I am talking about the structure happens to be the set of real numbers, and I am talking about dot as multiplication and plus as addition. Remember that we are given interpretations now, right? Once you have interpretations and you have some elements for this one depends on what value you give to x, y and z, right? So the moment you assign values to variables, I can evaluate terms. I can evaluate this term. X is some particular real number. Apply the function that you've got, you will get some real number. Remember, it will take some triples and produce this, right? So in this particular case, you can apply the multiplication function twice and it will get you a real number. And then do the same for this, you will get a real number, and then plus is the addition function, apply it, you will get a real number. Here, do the same, you will get another real number. If they happen to be the same, you say this is true, otherwise you say it is false. Is this clear? That's the name of the game. So, in some sense, what is going on is that the moment you gave me the parameters for the language and you gave me the interpretation, right? You've done the hard work. I just have to be like a machine. Oh, this is very nice, right? So that's really what we want to come to. Be like a machine, evaluate terms, applying the definition that you gave me, right? It's your problem if you gave me wrong definitions, right? You gave me certain definitions, I apply them, produce elements of the domain, and if they happen to be the same elements, I say yes, otherwise I say no. That's my job. My job is to say true or false, but strictly following your own advice. Is this clear? So let's formalize this process that I said, evaluation of terms. Right? So now, what have we got? We have got a structure S, which is a domain with an interpretation which we have defined. So this is what I call an L structure. Along with that, now I move to what I call a model. A model M is a structure along with an assignment pi which maps variables to values, right? Remember that I don't know what variables will pop up, x, y, z, anything you like. For every variable, I assign an element of the domain. That's what I'm supposed to, right? The whole idea is that, remember that variables denote elements of the domain. And this is called an assignment map or valuation, whatever you like. This is basically, I'm just saying that this is intuitively what we had in mind, right? I am just formalizing what we said. Now, this map that you have given me, the moment I have got an interpretation, what I can do is, this tells me what is the value for all variables. I lift it, let me call it pi hat, from terms of the language to the domain D. I remember that what did we just say? I have to evaluate every term. That means I have to pick a term T and assign it a domain element. How do I do that? Absolutely straightforward. What is pi hat of, well, what is the inductive definition of tau? Remember, constant symbol is a term, a variable is a term, and if k is a function symbol, I mean f is a function symbol of arity k, and t1 to tk are terms, so is f applied to this, right? So now I define pi hat as a map from tau to d, again inductively. What is pi hat of c? Well, it's whatever is the interpretation for a constant symbol c that you have got, that will be the element, right? Somebody has already told you what is the evaluation of a constant symbol. What is pi hat of x? Pi of x, right? Please get used to formal definitions if you are not. This is basically something intuitively clear. We are writing down carefully so that every term gets an element assigned uniquely. So what is pi hat of f of t1 to tk? Remember, this is the term that I am considering. Inductively, the terms t1, tk, they have all been assigned. So I take the tuple pi hat of t1, pi hat of tk. So this is what are these things? They are all elements of the domain. This belongs to d to the k, right? So now I apply some function to it. Which function do I apply? Whatever the interpretation is giving me. if of fk, if I like, right? This will give me a function that applies to any k tuples of elements of the domain. It will return an element of the domain, and that's it. Yeah. Now we have defined evaluation of every term. Now I can say that t1 equals t2 because I apply pi hat to t1 and I apply pi hat to t2. If they are both the same element of the domain, I say the equality holds, otherwise say the equality doesn't hold. Is this map clear? Right? Every term now in the language is assigned a unique element of the domain. So with that, we are actually, yeah, sorry. Somebody.
So what is this map called? Pi hat?
It's the evaluation of terms. It's again the assignment map. The assignment map is given on variables. I lift it to the set of all terms. Yeah. So call it assignment evaluation or whichever. Yeah. It's simply the lifting of the given map. It's a natural lifting that is given by so we have used so now notice that whatever is given we have been using religiously. That's very important, right? There should be no junk floating around, right? We have used the interpretation for constant symbols, we have used the interpretation for function symbols, we have used the assignment on variables, all of them have been used. One thing is left, what is that? The interpretation for predicate symbols. That will of course get used when we evaluate the atomic formulas involving the predicates. Okay. So can I erase this now? Let me. Okay. So now the main definition, the truth definition in the language, and this is the we say that alpha is true in M, or M satisfies alpha, or some, we call it by very different names, it doesn't matter, it's just a binary relation on not structures and statements like I said, it's actually between models and formulas. The set of all models, because once you have an L specified to you, right, you have an L structure that we have defined and you put an assignment, you get an L model. Now this relation is between the class of all L models and a set of all formulas of the language. And this is something that we define now. How do you define it? Inductively, because formulas are defined inductively, therefore the relation is also defined inductively. Okay. I'm going to take off some more things. Well, inductively, so defined by induction on the structure of alpha. Now, this is a term, this is a phrase you better get used to, right? In this course, we are going to be doing all the time induction on the structure of formulas, right? Different logics, different languages, different models, it doesn't matter. But so if there is one kind of a take home message to give in this business of giving semantics in logic, the key word is this. Somebody actually asked me this on mail. When do you say that a language is a... Sorry? Sorry?
The top of the board is not visible.
Is not visible. Okay, wonderful. Okay. Yeah. So I would say that I'll write it. Yeah, it's not a the way the meaning is built inductively, right? That's one of the most important things in logic, right? This is the principle of what is called compositionality, right? That you take a whole sentence, the meaning of the whole sentence is given by the meaning of the parts of the sentences. So the meaning is built compositionally. So that's why I said, somebody asked me on email, when do you say a language is a logical language? A logical language is one which has and, or, not quantifiers? Not really. Like I said, I would like to remind you of somebody who lectured with alpha, beta, and gamma, and so on, right? So you can write whatever stuff you like, and it's not even necessary that it must have, this combination of negation, disjunction, and so on. It's just that Boolean logic we are all comfortable with, that we begin with, right? You can have whatever connectives you want. You call it logical when you can build meaning compositionally, meaning inductively. This is the main reason, and that is in some sense what this whole business is about. So now we have models, now we have formulas, and we want to define the meaning inductively, or so this is what I was writing on the board, which you couldn't see. The meaning is built compositionally, right? So compositionality is in some sense the heart of the whole business. If you ask what makes a logic, well, meaning is given compositionally, right? And already it's clear that, so in this sense, formal languages, most formal languages are compositional, programming languages are compositional, and in fact, assigning meanings, semantics of programming languages is difficult mainly because of giving a compositional semantics. For anybody who has thought a little bit about programming languages and trying to give meaning to what a program does, right? I mean, we have experts like Purandar sitting here in the group. And so yeah, meaning is given compositionally, and that's not easy. When you have local variables, global variables, scope, it can be, compositionality can be very difficult, and that's one of the reasons why semantics of programming languages is difficult. When it comes to natural languages, and this is the real hard thing. So the relation between logic is also very closely related to linguistics, and one of the main things is that logic insists on compositional semantics, meanings to be built compositionally, and natural language is highly non-compositional. There is all sorts of things floating around in the background without which you cannot give meaning. You can't just assign meanings. No, you would like to, and that makes the whole exercise difficult. Okay, so let's just do this for our baby language that we have got. What is the, so defined by induction on the structure of alpha, by which, what does it mean? Remember induction on the tree structure of alpha, right? So that means, what is the base case? What's the base case for a tree?
Leaves.
Leaf
leaf.
node. Yeah, a node, a tree which has got only one node, right? So what kind of formula is that? That's an atomic formula. That's what we mean. That's why
Formula.
you always start with atomic formula. An atomic formula, so we say M satisfies T1 equals T2 if, well, when do you say T1 equals T2? We just said, right? This is any equation. Evaluate the left hand side, evaluate the right hand side. If they come out to be the same element of the domain, you are happy. If and only if pi hat of T1 equals pi hat of T2. Remember that our model is M is pi, and pi hat is the map. So pi hat is the lifting of the assignment or evaluation map to the set of all terms in the language. Once you have got this, now we can say that T1 equals T2 if pi hat of T1. Notice that there are two equalities here. What are these two? This is the equality in the language, right? This is what the language of equations that is built into the syntax of our language. This is an L equality. And what about this equality? This is the equality on D, on the domain. This is in our math book equality, right? Which means that these two come out to be the same element in the domain, right? And this is very important, right? Because we do write things like, these are different expressions. As terms, they are very different terms, right? It's just that they happen to evaluate to the same element always, and that is the sense in which we mean. Okay, fine. So in atomic formulas, is there any other case to consider? Are we done with atomic formulas?
So the predicate.
The predicate symbols. This is, you pick an Emery predicate symbol and you can apply it to M terms, then you get an atomic formula. And so when do you say this holds? Well, we know how to evaluate all these terms. So consider the tuple pi hat of T1. What is this? This is an M tuple in the domain, right? So now we want to find out if that M tuple is in actually the relation. Which relation? This belongs to D to the M, right? So what should I check for? Well, interpretation. Yeah, what's a big deal, right?
Sir.
Yeah.
Yeah.
So you apply the interpretation that you have got for predicate symbols on this particular symbol, it will give you a map. If that turns out to be equal to 1, because this is the meaning we agreed, right? The interpretation for the predicate symbol is given by this. That's a map from D to the M to 0 to 1, 0 or 1, and 0 means it is not in the relation, 1 means it is in the relation. So that's it. And this completely specifies the meaning of the atomic formula. So with these two, the meaning of the atomic formulas is done. Now we have to lift it to the other connectives, right, the more complex formulas. That's exactly the compositional sense in which we want to do this. Any questions on this? Note that already equation solving we are ready, right? Whatever we write with equations, you can. This is what equation solving is all about, right? So what is the meaning of, now the base case is done, that means we are looking at an arbitrary tree, right? Your formula alpha is a tree where, right, this is the induction step that we are considering, that means it has got a non-leaf node. If it's got a non-leaf node, what should that non-leaf node be labeled by? Remember, when you think of a formula as a tree, it's got some leaf nodes, some non-leaf nodes. Non-leaf nodes means it should be labeled by, somebody said, a connective or a quantifier, please, yeah? It could be a connective or a quantifier. If it's a connective, it can be a unary connective or a binary connective. What's the unary connective we have got?
Negation.
Yeah. Okay. Yeah, negation. And so here, so alpha is of the form not beta. When do we say that not beta is true in the model M? How do we define this?
If beta is not true in M,
That's true. But how do I go around checking whether beta is true in M? But that's the whole point about doing by induction. The induction hypothesis tells me beta, remember, this is the tree that we are considering. This is a smaller tree than the original one. So I know how to check for whether this is in the relation or not. Remember that the entire relation between the class of models and formulas is being inductively defined. So given any model and any simpler tree, I know how to evaluate it. So this is all I want to write. So if and only if this pair M beta does not belong to the relation, right? This is what we are saying. This part is already defined. Whether this is in the relation or not is inductively defined. Now I just look at it and say this. Now this is an awkward notation. So instead of that, we will write this looks like tricks. There are no tricks. This particular not beta, this is what we are actually writing. M comma not beta belongs to this relation if and only if is not in this relation. This is really the content of what we are writing. And this is perfectly all right. There is, no sleight of hand involved because this is something simpler and the complex one is being defined in terms of something simpler. Is this clear? Yeah? Any question on the notation? This is the notation that we are going to follow. Anybody, any questions? Otherwise, now it should be clear that this whole thing will lift up quite easily for everything else. What is, when do you say alpha and beta holds in the model M? Again, what is this? How is this represented? This is a tree which has got a non-leaf node labeled by conjunction and two subtrees alpha beta. Inductively, we know whether alpha is true in M or not, beta is true in M or not. So how do I make use of that? What should I write on the right hand side?
M is a model of alpha and M is a model of beta.
That's it. Now, what is this and here? This is the whole point, right? We are doing this whole business in our own English or Bengali or Tamil or whatever, right? So this is the our and, right? The natural language and this is what we mean. This is just a representation of this relation. We know whether this pair is in this relation or not, this pair is in this relation or not. We know what this and means and we write. That's it. Yeah. Of course, then it's also clear what this means. And this is the, what kind of OR is this? This is not the English and Tamil and Bengali OR, right? This is the mathematical OR, right? Yeah, I mean, will you have coffee or tea? What do you say? You say yes. And am I allowed to give you something mixed with both coffee and tea? I mean, come on, that would be crazy, right? Mathematicians have no problem with that, right? So this is the mathematical OR. So, and by the way, George Boole, I hope you have, George Boole, who started this whole racket in some sense, right? This propositional reasoning was extremely bothered by this, right? So, in fact, he spent an enormous amount of his work trying to make sure that you use only exclusive OR, because exclusive OR is what we use naturally. And it was a matter of immense botheration to him that he couldn't do what we call Boolean algebra, which he didn't call. I mean, the kind of algebra that he wanted seemed to require this inclusive OR, right? So, if you read George Boole, I hope you will. So, which book of Boole that I am talking about? The Laws of Thought, nothing less. Okay, can you imagine some? Yeah, it's a very slim book. I'll send you the PDF if you want. It's there all over the internet, and an investigation, a mathematical investigation into the laws of thought. How grand, right? And if you see, he is deeply bothered by this whole exclusive OR business, right? Because exclusive OR is what we normally use, but this OR that we are using is the mathematical OR. That means either alpha is true in M or beta is true in M or both. That's okay. So the only way alpha or beta, that is junction, is false is when both of them are false. I mean, we are used to Boolean logic, propositional logic, we consider it natural, but I am just rubbing it in that this is. What about implication? What's the meaning of this? If M makes alpha true, it better make beta true, right? Whenever alpha, is this visible below? Yeah. This is what, and I have written something really vague. Somebody was objecting to my writing vague statements and so on, right? I insist on being vague because, as I said, math books have no problem writing these things, right? I mean, we think we know what this means, right? If you and I can communicate, that's all this language is. The right hand side of the if and only if, the left hand side is the formal relation being defined. As long as I define it inductively and we can all agree on what the meaning is, I am fine with it. So I like statements of this kind, right? If, or we can write, if M makes alpha true, it better make beta true. That's perfectly fine because I hope it's very clear what we mean. What we mean is really, it is not possible that this holds, but this does not hold, right? This is really the meaning that we have in mind, and if you want, you put that in, if and only if. It is not the case that there is a double negation there. For those who rejoice in double negation, this is good, whichever you like, right? But I hope this meaning is clear. Then we have alpha equivalent to beta exactly when either both are true, or it makes the model M makes alpha true as well as beta true, or it makes both false. It's not the case that one of them is true and the other is false. This is the intuitive meaning, and you can write. And usually it's much more fun to write like this, to say, oh, this if and only if is different and so on, right? It looks like sleight of hand, but it's all very clear. So the meaning of connectives, as I said, I mean, all of us know Boolean logic, it's very clear. Let's get to the interesting one that is left, which is quantifier. Okay, so let me take this off. Yeah, now somebody has to help me. Who's going to help me with this? Sabarish, can you tell me what I should do for? Not there? Okay. Who else? Yeah, somebody tell me what I should write here. What is the intuitive meaning of for all x alpha?
So sir, like when we inductively go down to, when we're interpreting and we go down to a single variable.
This is the picture.
And we apply, and we apply pi hat to that, and like we apply at the end we apply pi hat to that.
Pi hat to which? Pi hat applies to terms. Pi hat applies to any term in the language. A variable is a term. So in fact, you don't have to go to pi hat. Pi gives me the meaning of for a particular x. This is for all x.
So like wherever there is that variable x in alpha, and we ultimately have to apply pi to that variable. So if even after applying pi hat to all the elements in the domain.
Okay.
Still the formula.
So this is when we say this, we mean for all elements in the domain. For all choice of x as an element of the domain, right? For all, when we write for all x, what we mean is that for x, we are allowed to choose any value in the domain. Try every possible value in the domain, and somehow that application of pi with that element should make alpha true. This is the sort of thing we are saying, right? So this part is easy for all, and then what Swapnil was talking about was, I go down to alpha, somewhere x occurs, right? For x, some d that you have picked, right? Try for that value of d, right? This is what he is saying. Anybody has any? So maybe I can write it like this. We'll define this, but this says that take every occurrence of alpha substituted, every occurrence of x substituted by d, right? I go to alpha, wherever x occurs, instead of that I replace by d, and then check whether this new formula holds in the model M. Is this okay? I know that we need to define this, but you know what this means, right? I go down to the formula, so I try. If it's natural numbers, I try with 0. I substitute 0 for x throughout and check. Then I try for 1. Then I try for 2. I go on trying for all of them. If all of them, the substituted formula is true in the model M, I say that for all x, alpha holds in model M. Is that reasonable? Okay, now I need a show of hands, since I don't know whether it's reasonable or not. Right? How many people think this is fine? Okay, I see some hands up. Only one approval so far. Come on, 2, 3, 4, 5, 6. Okay. Anyone else? Kamalika, I don't. Your hand is kind of half up. Okay. Okay. What about Aditya? And all those dark people whom I can't see, God knows whether their hands are up or down. Okay. Anybody thinks it's not okay? There is actually a problem in this. What is that? Remember, what was D? This D is an element of the domain, right? What is the domain? What kind of elements live in D? So D is a set of what? Yeah. What is D a set of? D is a set of anything, right? We have no idea what lives in D. I usually say that D is a set of goats. I don't care, huh? It's some, right? One thing you cannot do is to substitute for a variable. You can't put a goat in a formula. That's not allowed. The set of formulas does not include goats and such animals, right? What can you do in formulas? What are the things that formulas are made of? Terms. Terms have constant symbols, function symbols, predicate symbols, variables, connectives, quantifiers. That's all your formulas are. I cannot go around and substitute. This is very important, okay?
Sir, but x is also a goat.
X is a variable, X is not a goat. X is a syntactic creature, right? X is not a goat. And this is the important point, right? When I write 0, I don't have to write quotes, right? A constant symbol 0, right? Remember that this is a word that represents the number 0. This is a syntactic object, right? This is not a syntactic object. The semantics, the meaning can be as complex as you like, right? The words in my language are something very disciplined, right? So this is very important, and this is very for a particular, let's say that, I mean, this is something you want to work with, right? You do want to work with real numbers. Remember, last time I talked about the cardinality of the language. What's the cardinality of the set of constant symbols? What did we assume? Countable. We said countable supply of constant symbols, countable supply of function symbols, countable supply of predicate symbol, countable supply of variables. So, what's the cardinality of the set of terms? Countable, huh? There are only countably many terms in my language. Okay, let's get to formulas. What's the cardinality of atomic formulas? Well, pairs of countable sets, equality, surely countable. Well, you can write P T1 to Tm, that doesn't matter. Finite sequences of elements of countable sets. So the set of atomic formulas is countable, and then you close under connectives, the whole thing is countable. the set of formulas, so the language L is countable. Cardinality here is cheerfully can be uncountable. And who says it's R? Huh? Why not R to the R? I mean, what's stopping me from picking some set in the Cantorian paradise and, of whatever cardinality I like, right? So, you may not, when I say it's a goat, take it very seriously, right? You may not be able to substitute it by a syntactic element, right? You may not even have names for all the elements in your language, right? So, you may not be able to set a map like this. Remember, the interpretation goes the other way. Every constant symbol is interpreted as an element of the domain. You may not have a map which actually gives me name for every element in the language, right? So, you can't say that what I will do is not put D here, but some name for D, right? It simply may not be there in your language. So, we can't write such things at all. So, this project, I am afraid, is dead. We'll have other things to take care of this, but the meaning is actually given by, well, there is a slight difference, right? Yeah.
Sir,
Yeah.
sir, what if we restrict our domain to countable sets? Because
Then of course,
to define
then of course you can do, but we don't want to. I don't want to. I want to work with reals. I mean, come on. Remember, we do want to write for all x there exists y such that, right? I do want to talk about its truth and stuff, right? So, not fair. Yeah. I mean, come on. You started the project like describing all of mathematics, and the first thing you say is, I'm going to, the structures of interest are only countable sets. That's not funny, right? No. But that's because this is a very simple bureaucratic change that is needed. That's all. The answer is very simple. What I do is, well, I can't go around putting goats inside formulas, but I can put goats inside models. Models are rich, no problem. So, this is how I write it, and I will write it and describe it to you. If for all D belonging to D, what I look at is M prime satisfies alpha. Let me call it M prime D satisfies alpha. So, in particular, M prime. I go over to a different model. What is that model? It's the same as model M, except that the new model is going to make sure that x gets a value D. In this model, alpha holds. Okay. So, what is that? So, M prime xd equals, what was M? Remember, M was this, the structure S and the assignment pi. So, this is S comma pi prime, the same structure. I am not changing the interpretation for any of the parameters at all. I only look at the assignment which is slightly different. What is pi? Pi prime? Pi prime is a map from variables to domain given by pi prime of y equals pi of y if y is not equal to x, d otherwise. Can you see this? Should I write it in the middle? Is it clear? What is this saying? Pi prime is the same map as pi everywhere except at x, where it is given d. So, this you would call the variant of the this is a model variant. You take the same model, vary it just a little, right? Where you have changed the meaning, you have not changed the meaning for anything else except that for the value for the variable x, you try the value d. In that particular model, note that inductively this is defined. Why? Remember that this relation is being defined for all models and all formulas, right? So, inductively this is a smaller formula than what I began with, and this is some decent model. It is a perfectly decent model, so I can check if it is true or not, and this is what I do. And this is in some sense what we actually do, right? So, even though that idea of substituting, going around substituting in formulas makes sense, but in general what we actually are thinking of are, I am looking at taking the variable x and assigning it different possible values. Each time I get one new pi, right? I get pi 0 when I try 0, pi 1 when I try 1, pi 2 when I try 2, and so on in the language of arithmetic. So, and this, who cares about cardinality here, right? Do as you like, right? Remember that it is mapping into D, and D could be some bizarre thing. We don't care, right? And if D was actually goats, we are actually trying the first goat and the second goat and so on, right? No problem. So the meaning of the existential quantifier is absolutely straightforward. Once you have got the thing on the board, there exists x alpha if and only if for some D belonging to D, m prime x D satisfies alpha, where the variant already is defined. This is a definition. And that's it. Now we have defined the meaning of all the formulas, we are done. Right? So now given any particular model M and a formula alpha, we can say whether alpha is true in M or not. Okay? So as usual, whenever a definition is presented, and this is again part of the culture, the moment somebody gives a definition of this kind, there is an algorithmic question that comes. What is the algorithmic question? So fix natural question. Somebody gives you a model, somebody gives you a formula alpha and asks, is alpha true in M?
Sir, the upper line is not visible.
Very good. Yeah, so I'll write it here. Is it visible below here?
Yes, sir.
Okay. So fix L. Yeah. But for it to be an algorithmic question, I have to present the input, right? What are the inputs here? There are two inputs. L is fixed for the whole algorithm. That means the vocabulary is fixed. So I'm assuming that this is a finite vocabulary. There are finitely many constant symbols, finitely many function symbols, finitely many predicate symbols, right? So that's already fixed for me. And I give you a structure, an interpretation for all these symbols, and an assignment map, and I give you alpha. So what are the inputs now for me? The model and the formula alpha. Now how is the model presented to you? Okay, it has to be given as an input at all. So what is of interest here? When do we say that the model is finite? Well, the domain D is finite, right? I give you the domain D, which is a finite set. These are all finite vocabulary, and I ask you whether a formula alpha is true. So your algorithm is now supposed to, alpha is presented as a tree. It's supposed to traverse the tree, do whatever evaluation it has to do, figure out, and come and say whether it is, answer is yes or no. So think about this. How such an algorithm will proceed? What is difficult or easy about this? Remember that what's a model? A model is going to have a structure. Structure is finite now because the domain is finite. There are only finitely many constant symbols. So the interpretation for constant symbols is finite. There are only 3.5 function symbols. For them, you have those functions associated. That's also a finite description. There are only so many predicate symbols, 4 or 5 or whatever. Their relations on the domain. Everything is finite. What about pi? It's supposed to, what is pi? It's a map from what to what? Variables to elements of the domain. Now, variables is a countable set. Pi is not a finite object. For that, one simple thing is to look at alpha and see what are the variables mentioned in alpha. If a variable is not mentioned in alpha at all, what do I care? Right? Okay, so there is some bit of work needed. But if you make all that finite, then this question takes off. But we still have to write an algorithm, and then we have to look at its running time and think about how such a thing will proceed. But we have got all the elements here. There is an inductive definition. This tells you to evaluate this node, I go to the subtrees, evaluate them. In fact, you can evaluate them in parallel. Nothing stops you from doing it in parallel. You can keep on doing that until you get to the atomic formulas. And for atomic formulas, you have to evaluate terms. So your algorithm will somehow have to evaluate all the terms, and then you can start applying. Okay. So think about it, and we'll take it up next time. And so this is the main truth definition. So now we have got syntax, semantics, we are in business. Okay. Yeah, thank you.